Welcome to this presentation on Structural Analysis 2. In this session, we will study influence lines for indeterminate beams, with particular emphasis on determining the influence line for the reaction at support A in a continuous beam. Today, we are constructing the influence line for the redundant vertical reaction at support A of an indeterminate continuous beam. The structure features three roller supports labeled A, B, and C, forming two continuous spans that each measure exactly 5 meters, totaling a length of 10 meters. Our goal is to systematically calculate the precise influence line coordinates across the beam at uniform 1-meter intervals. We will use foundational structural mechanics to determine how a moving unit load dynamically changes the load distribution on support A. Let's step through the analysis. To find the influence line for the reaction at A, we apply Breslau principle. We begin by removing support A to release the redundant reaction constraint. Next, we apply an upward unit force directly at A, setting Ra equal to 1. By taking static moments about support C, we balance the system to find that the reaction at B, Rb, equals -2, and the reaction at C, Rc, equals 1. According to the principle, the true influence line coordinate at any point x along the beam is the ratio of its local displacement, yxa, divided by the total displacement at support A, yaa. We establish our positional variable x starting from the rightmost support, C. Using Macaulay's method, the bending moment at an arbitrary section is written as mx equals rc asterisk x plus rb of x negative 5. Substituting our calculated reaction forces simplifies the second-order differential equation to negative x plus 2x negative 5. Integrating this curvature expression once provides our slope equation, along with our first integration constant, c1. Integrating a second time yields the comprehensive deflection equation for the beam, introducing our second integration constant, c2. To determine our constants, we evaluate the rigid boundary conditions at the real physical supports. Since support C is unyielding, deflection is 0 at x equals 0, proving that constant C2 equals 0. At intermediate support B, deflection is also 0 at x equals 5, giving us a value of 4.167 for constant C1. To find the total deflection at support A, we evaluate our equation at x equals 10, resulting in negative 83.33 over EI. Dividing our generalized deflection equation by this total displacement yields our final clean influence line formula for Ra. By substituting our consecutive 1-meter increments into the final formula, we map out the complete influence line. Starting from support C, the coordinates enter a negative zone, dipping to a peak minimum value of -0.096 at 3 meters before returning to 0 exactly at intermediate support B. Crossing into span BA, the values turn positive and rise steadily up to a maximum value of 1 directly over support A. This graphical diagram provides a powerful visual tool, indicating exactly how moving loads induce downward uplift or upward reactions at support A. Thank you for watching this video on structural analysis.